It is the 24th of August, 2025, approximately 10:13 a.m. We're going to pick up where we left off with the preliminaries in Dummett and Foot. So, this seems stable enough. That's what I have to work with for today. We left off with the calculative on the Chinese remainder theorem. So, let's just look at a corollary. Corollary. You look at the multiplicativity, there you go, of this, of what we evaluated with the Euler-Totient function. If the GCD of AB is equal to 1, then Euler's totient function of AB tells us, well, it is equal to the totient of A times the totient of B. Now, it's not what the Greek letter is called, I know, but it's Euler's totient function, not the other thing. Okay, so by theorem, the reduction map of the integers over A times B integers to the cross product. This is getting into some things which I haven't really covered yet, but we'll get there. It'll all make sense. Okay, times. And then that there divided by but similar. Okay, by the theorem, the reduction mapping from the integers over AB integers to the Cartesian product. The Cartesian product from the integers over AZ and integers over BZ, which is the integers. The reduction map that and the equivalence class X sub AB to the ordered pairs of equivalence classes, roughly speaking, is a bijection of rings. So this is foreshadowing what we're going to be getting into later, and I'm kind of avoiding some of the terminology for this. This is very, so just to sort of show what we're going to be getting into. It's a prelude, if you will. Some of the things that we're going to be getting into within Dummett and Foot. I'll just show this, and we'll try and cover up as much of the, I guess, more complicated inner workings of the thing that will be delved into in later chapters. There's certain things that I can't really say about what these are because we haven't really talked about that. So, and that, but I'll use phrases to sort of delineate what they are in reference to what we currently have knowledge of until, well, not we as a species, but where we're currently at. So this is a bijection GCD AB equal to 1. Now, a bijection of rings, a bijection of rings, sorry. Of rings. What is a ring? We'll pause on that for now. We'll get back to it. The bijection restricts to a bijection of unit groups. And we'll get into what those are as well. But just to sort of ease us into what's going to come, that's basically what we're doing here. I'm not used to this amount of board space yet, but I'll get used to it. Restricts to a bijection of unit groups. And these, of course, being represented as such. The integers over AB times the integers times the integers. And the Cartesian product basically that we had earlier, but with this little notational difference right here. Just keep the notation in mind. What we're seeing will be explained. It's just that for now, just sort of see the inner workings of these very basic things in comparison to what we're going to be doing, which is building up theory upon it. And all of this stuff has different wording that we'll get to. So taking cardinalities, yields, and there's a lot more simple way to prove this, of course. It's just we're using this for now. Like if you ever take like a applied modern algebra course, or a number theory course, there's definitely a lot more less top-down approach to solving this, I'd say. Yields that the totient function of AB is equal to the totient function of A times the totient function of B. And there we go, what we wanted. Now let's look at something a little more concrete. We've taken a glimpse at what lies ahead in chapter 1. Now let's just come back down to earth. So, here's a proposition. Check the camera real quick. Camera's looking fine. These are the values of the totient function. So, if P is prime and alpha is greater than or equal to 1, then we'll have that the totient function of P to alpha is equal to P to alpha minus P to the alpha minus 1, which is equal to P to the alpha minus 1 times P minus 1. If the GCD of AB is equal to 1, then the totient function of AB is equal to totient function of A times totient function of B. So it says a lot more there. We've got two if-then statements. It's a big deal. 100% more than just one. Yeah, let's get into proving that. Yes, okay. So, for P to the alpha, the integers 1 all the way up to p to the alpha are divisible by p are the integers 1 to the p alpha divisible by p are p reasonable to p reasonable all the way up to p to the alpha minus 1 times p, which is what? It's exactly p to the alpha minus 1 of them. So subtract from total p to the alpha to get totient function of p to the alpha. Right? So for multiplicity then, multiplicativity, by the Chinese remainder theorem, not critical something theory, but Chinese remainder theorem, reduction mod A and B is a bijection. Is a bijection defined by what? Well, you looked at this earlier. Just a little notational thing right here that I'm keeping a secret for now, I guess you could say, but I mean, you can just look forward in the book and you can see it. Intimidating at first, but once we get to know them better, not so much. Just like people in a way, you know? Okay, just less complicated. Or more. I don't know. Just sort of depends on the person. People in general. I'd say this is less complicated than people because people came up with this, you know. Okay. All right. Which by our lemma that we looked at earlier proves that this is the case. So we can say that the proposition we had that we were intending to prove is proved. Let's go ahead and look at another calculative. So, let's say we want to count the totient function of n by hand. For n is equal to 12, let's list 1 less than or equal to a less than or equal to 12, coprime to 12. Now, fairly enough, that's 1, 5, 7, 11. All right. So, which means the totient function of 12 is equal to 4. 1, 2, 3, 4 numbers, ergo it's 4. Now, for n equal 18, what we wind up getting is the set 1, 5, 7, 11, 13, 17, and there we go. So, the totient function, the totient of 18 is equal to 6. So let's check with the formula on this one, right? We have this beautiful thing. Let's test it. So 18 is equal to 2 times 3 to the power of 2. So 18, the totient function of 18, that is to say, is equal to 18 times 1 minus 1/2 times 1 minus 1/3. And what does that get us? Well, that gets us 18 times 1/2 times 2/3, which is equal to 6. So there we go. We looked at the logical consistency beforehand, and now we have shown concretely that it works. Now, let's move on to another calculative. So, we have our calculative for multiplicativity of the totient function with coprime inputs. So let's suppose that A is equal to 8, B is equal to 15, and that, well, we know the GCD of 8 and 15 is equal to 1. Now, the totient of 8 is equal to 4. Now, evidently, we can see these as 1, 3, 5, 7. And for 15 equals 8. We'll just exclude, in which we just exclude multiples of 3 or 5. Now, what this means is that the totient function of 120, which, 8 times 15 equals 120. With what we've seen earlier, this should be equal to totient function of 8 times totient of 15, which is equal to 32. So let's check that directly. Well, 120 is equal to 2 to the power of 3 times 5. So the totient of 120 should be equal to 120 times 1 minus 1/2 times 1 minus 1/3 times 1 minus 1/5. And what this gets us is 120 times 1/2 times 2/3 times 4/5, which is equal to 32. So, there we go. Camera's still working. Very good. Let's look at another calculative. which is the totient on prime powers. So for p is equal to 3, alpha is equal to 2, we have this totient 3 squared is equal to 3 squared minus 3 to the power of 1, which is equal to 9 minus 3, which is equal to 6. And what's interesting is that among 1 all the way up to 9, the 6 coprime to 9 are 1, 2, 4, 5, 7, 8. So that's an interesting thing right there. Let's see how much time we have left. Plenty. So we're going to go ahead and move on to discussing the integers modulo n, which is what I was obfuscating in the beginning. Because, well, now here we are. Complexity of discussing things without the encapsulation of more verbal structuring leads to a sort of wandering around of discussing this as something which takes up a lot of air. So this integers over n times the integers, basically what that's what it literally, literally looks like. But the integers modulo n, that's what we'll refer to this as. Now, historical context: the study of integers modulo n began in earnest with Carl Friedrich Gauss's Disquisitiones Arithmeticae in 1801. Probably butchered the pronunciation. Oh well, Gauss introduced the notation A, this notation here, A equal to B mod n, and built a systematic theory of congruences. Yeah, that's what this is, congruence. Congruent to, A is congruent to B mod n. And built a systematic theory of congruences. The idea itself is older. The Chinese remainder theorem dates back to Sun Zi from the 3rd to 5th century AD. And modular methods appear implicitly in work by Euler and Fermat. Today, the integers modulo n, the set of residue classes modulo n, just a better way of saying this, residue classes so that means I might have misspoken there earlier. Modulo n, might have misremembered, is fundamental in algebra, number theory, cryptography, and coding theory. I've mentioned cryptography and number theory. Coding theory is part and parcel to that stack of things, but it allows us to treat numbers that differ by multiples of n as the same for arithmetic purposes, forming a finite ring. So, let's have a definition of congruence. Modulo n. if we let n be a positive integer for a, b within the integers, that are also integers, we say a is congruent to b mod n, and this is written as these three lines, congruent b mod n. If n divides a minus b. Equivalently, a and b have the same remainder, upon division by n. Right, let's check the camera again. 56. So let's start with congruence. Let's start with a proposition, I mean to say. Congruence mod n is an equivalence relation on the integers. Proof. Well, let's check each of the three properties that we expect from an equivalence relation that define an equivalence relation. Reflexivity a minus a is equal to 0 is divisible by n. Just the other way around you got to worry about. Symmetric. Let's suppose we have n divides a minus b. Well, then we can say that n does divide b minus n. I mean a. Transitive. Okay, suffice to say right now. A transitive. N divides a minus b, and n divides b minus c implies that n divides a minus b plus b minus c, and that this is equal to a minus c completes our proof. Now, let's look at a calculative example of this. A calculative. Checking congruency two ways. So let's suppose that n equals 7, a equals 51, and b is equal to 16. Now, a first method is to look at the divisibility of the difference. Well, what do I mean by that? Well, so a minus b is equal to 51 minus 16, which is equal to 35. Now, 35 is equal to 7 times 5. 7 divides a minus b. So, 51 is congruent to 16 mod 7. Fair enough? Let's get to method 2. Method 2. We look and see if we have the same remainder upon division by n. Division by n. So, we looked at the division algorithm, and so we have that in the back of our minds, but by the division algorithm, we find that 51 is equal to 7 times 7 plus 2, and 16 is equal to 7 times 2 plus 2. Right, so both have remainder 2. When divided by 7. Very good. So, what does this tell us? Well, 51 is, did I say 3 methods at the beginning? Yeah, I must have been. 51 is congruent to 16 mod 7. Now, these two methods agree. Congruence modulo n can be verified either by checking that n divides a minus b, or by comparing remainders. So you've got 2 routes, 2 roads. They all lead back to congruency Rome. All right. Now, let's talk to the thing of more major abstraction, which is residue classes. About that funny little piece of notation we had there at the beginning. So, residue classes and is here. The set of all residue classes. Z modulo n. Residue class? Yes, okay. So, the residue class of integers, of an integer a mod n is equivalence class sub a, which is equal to the set of integers b, such that b is congruent to a mod n. The set of all residue classes is denoted by this over here, where you have the integers divided by n times the integers. N integers is the best way I have of saying it right now. So, which is these equivalence classes here, 0, 1, and there's probably a better way of saying that as well, but I'm just going to hold on to that until I realize my mistake, and then I'll go back and fix it. Okay. These are all the residue classes. These are all the residue classes. Yes. Let's check the camera, check the time. Okay. Still got a lot of time to work with. A lot can be done in about 10, 15 minutes. If I can keep going that long. Heat's not working, so cold's not working. Let's look at what this means more concretely with a calculative example. Which looks at residue classes mod 5. So let's look at the set of all. Let's look at the set of residue classes mod 5. Set of residue classes. Set of residue classes. Yeah, sure. 5. Now these are 5 classes. These are 5 classes. These, of course, being 0, 1, 2, 3, 4. Each residue class 0, 1, 2, 3, 4. For instance, residue class of 7 with respect to 5 is equal to, the residue class of 2 with respect to modulo 5. Since 7 minus 2 is equal to 5 is divisible by 5. Fair enough.